We're going to talk about series now. This is the way we denote a series. We use the capital Greek sigma, and we read that as a sum from n equals 1 to infinity of the terms a sub n. So it's just like a sequence, only instead of just listing the numbers, we're adding them all together. So somehow we have an infinite list, a1, a2, a3, a4, a5, going on and on forever. And we want to know, what does it make sense to add all of those together? It's important to ask that question, does it make sense? How do we make sense of this? Because, well, any kid can add 17 numbers together or 112 numbers together, but what does it even mean to add an infinite number of numbers together? Right away, we should see that if we look at something like 1 plus 1 plus 1 plus 1, etc., and we keep adding 1 to itself over and over again, that won't make any sense. It will, we use the term in mathematics, blow up. It will not be equal to any finite real number. And we would write that in series form as the sum from n equals 1 to infinity of 1. That means when n equals 1, we have 1. When n equals 2, we have 1. When n equals 3, we have 1, etc., and we're adding those together. We say that this diverges, and we'll give a more precise definition very shortly of what that means. When a series diverges, that means we can't assign any value to it. You can't say that this sum has any particular value at all. Let's make these definitions precise. So here we have a series, sum from n equals 1 to infinity of a sub n. That's a1 plus a2 plus a3, etc. In order to make sense of it, what we're going to do is look at partial sums. So we define S sub n, this is what we'll call the nth partial sum. And that will just mean the sum of the first n terms. Of course, that will make sense. You can add n numbers together, any finite number of numbers, you can add them all together. Then we say that the series here converges exactly when this sequence of partial sums converges. In other words, what do we mean by this series? It means we basically add the numbers one at a time. We start with a1, then we look at a1 plus a2, then we look at a1 plus a2 plus a3, and we keep adding more and more terms on. And if when we do this, the things we get, which are exactly these partial sums here, if those things we get closer and closer to one particular number, in this case, we'll say if this limit of these partial sums is the number s, that means that these things get closer and closer to capital S, then we say that the value of the series equals s, and that the series converges. Sometimes you might say it converges to s, but normally we would just talk about the value of the series is s, or say the sum equals s. On the other hand, if this sequence of partial sums if it diverges, in other words, has no limit, then we say that the series diverges and it's impossible to assign a value to it. If we go back over here to this example, the partial sums s sub n, that's just 1 plus 1 plus 1 plus 1 n times. That's just n. And of course, the sequence n, we've already seen this sequence diverges. There's no limit. The sequence grows without bound. So these are the most important definitions, and it's going to be extremely important that you understand these definitions in order for everything in chapter 11 to make any sense. Let's look at a very interesting example of a series, and there are several other videos that I've asked you to watch for this same section, which involve talking about series that are very much like this one. But I'll talk about this one just for a couple minutes anyway. Does this series, the sum from n equals 1 to infinity of 1 over 2 to the n, converge? And if it does, what is its value? We'll often ask this question. because in order to talk about the value of a series, we need it to converge. So the first question is, does it converge or does it diverge? If it diverges, there's no notion of value that we can give to it. But if it converges, then we sometimes will be able to find the exact value for the series, and many times that's interesting. Now, what does this series mean? Well, we can think of it as 1/2, that's 1 over 2 to the first power, plus 1/4, plus 1/8, plus 1/16, etc. Does this series converge to any particular finite number? Well, what are the partial sums? Let's list a few of them. S1, that's just 1/2. That's the sum of the first one term of the series. What is S2? That's the sum of the first two terms. That's 3/4. 1/2 plus 1/4. Move this over a bit. What is S3? That's 1/2 plus a fourth plus an eighth. That's 7/8. What's S4? When we add the first four terms, we get 15/16. It's pretty easy, and try to convince yourself of this formula, that S sub n, the nth partial sum, is exactly 1 minus 1 over 2 to the nth power. In other words, this is 1 minus 1/16. That's 1 minus 1 over 2 to the fourth power. This is equal to 1 minus 1 over 2 to the third power. In general, S sub n is 1 minus 1 over 2 to the n, so this sequence, S sub n, converges to 1. In other words, the more and more terms you add here, the closer and closer you get to 1. And because this sequence of partial sums has limit 1, we say that the sum from n equals 1 to infinity of 1 over 2 to the n is equal to 1. So when I say a certain series has value 1, that means exactly what I said here, that the sequence of partial sums converges to 1. Let's look at this other series. This series has a name. It's called the harmonic series. And it's just 1 plus a half plus a third plus a fourth plus a fifth, etc. We can ask the question, does this series converge? And here it's not so obvious. It's actually very difficult, and there's in fact impossible, to get any nice formula for exactly what S sub n, the nth partial sum, is. So here we can write S sub n, that's just 1 plus a half plus a third, and go all the way up to 1 over n. Hard to tell exactly a nice formula for that, so it's hard to tell whether that sequence converges or diverges. But there's going to be a different way we can try to understand this. So I'm just going to erase this part here. And I want to draw a few more things here, like 1/6 plus 1/7, 1/7 plus 1/8 plus 1/9 plus 1/10 plus 1/11 plus 1/12. You might wonder, why am I writing out so many? Well, of course, there are an infinite number of terms, so I could go on like this, not just for a long time, but literally forever. That should be enough. And I'm going to ask, how big are the partial sums as I add more and more terms to this sequence? Well, I'm going to show you a very interesting way to split things up. If I add them in groups like this, what can you say about each of these groups? Well, this here, we have exactly 1/2 here. This is something bigger than 1/2. I claim this one is also bigger than 1/2. Because there are two terms, and 1/4 is the smallest one. This one's bigger than a fourth, so this is bigger than 1/4 plus a fourth, which would be a half. In this group, I have 4 terms. The smallest term is 1/8 here, And since that's the smallest term, and I have 4 terms, the total will actually be greater than 1/2 there. In this group, I have 8 terms. This one, not including the 1/17 here, it's stopping there. I have 8 terms, and 1/16 is the smallest of them. So when I add them together, I have more than 8/16, which means I have greater than 1/2. Now, I claim this pattern can continue forever in the following way. If I stop where here I have 2 squared, this is the 4th term, or I'll write n equals 2 squared, which I didn't write clearly. Here I'm stopping at the n equals 2, the 2nd term. Here I'm stopping after 2 cubed terms. Here I'm stopping after 2 the 4th terms, etc. Each time I go from one power of 2 to the next power of 2, they're exactly 2 to the n minus 1. In this case, there are 2 squared terms. Here there are 2 cubed terms, etc. When I go between 2 to the n minus 1st power and 2 to the nth power, there will be 2 to the n minus 1 terms, and the smallest of them will be 1 over 2 to the n. So when I add them up, they're bigger than 2 to the n terms times the smallest, which is 1 over 2 to the n. The sum will be bigger than 1/2. So what does that mean? That means when I add up all the terms all the way up to, in this case, 2 to the 4th, what do I get when I add the terms all the way up to this 16th term? That's what we call little s sub 16. That will be, I can't tell exactly what it is. It's a messy number, messy rational number, but I know it's bigger than 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2. Here I have exactly 5 halves. If I went out to the next power of 2, s sub 32, I would have another half, so I would have that be greater than 6 halves. S sub 64 would be greater than 7 halves, etc. In other words, the 2 to the nth partial sum, not the nth partial sum, but if I go all the way out to 2 to the n, this pattern continues, and that would be greater than, I would actually have n plus 1 over 2 here. And what does that tell us about this sequence, S sub n? What it tells us is that it diverges. Why? Because these partial sums, when I go far enough, they get arbitrarily large. They're not going to converge to any one number. If I go out to 2 to the millionth, which is an amazing number of terms, my partial sums are bigger than 1,000,001 over 2, so they're bigger than 500,000. If I go out to the 2 to the 2 trillionth, I'll have partial sums that are bigger than 1,000,000,000,000. I can make those partial sums as big as I want. They won't converge to anything, so the harmonic series, sum of 1 over n equals 1 to infinity, this diverges, and there's no way we can assign any number to it.